The introduction of the scientific paper focuses on the calculation of transition energy barriers and the characterization of activation states for the steps of fusion in biological membranes. It highlights the importance of understanding lipid movements and reconfigurations in membrane fusion and the consensus on key lipid intermediates in the process. The structure of stalks and hemifusion, as well as the formation of fusion pores, are described as crucial steps in membrane fusion. The authors mention that previous studies have provided insights into the energies and minimizations of these intermediates but have not determined an entire least energy pathway. The introduction introduces the string method as a practical and reliable method to calculate the pathway of least energy between two energy minima. The authors state that continuum methods, despite lacking granularity, incorporate the events needed to initiate topological changes and provide explicit calculations of deformations and energies for both proximal and distal monolayers. They highlight the advantage of continuum mechanics in making direct contact with experimentally controllable variables. The introduction concludes by mentioning that previous continuum mechanical calculations have obtained the shape of a stalk and a fusion pore of minimal energy, but the current study aims to calculate the entire least energy pathway of membrane fusion. The approach used in the study is described as providing a movie of lipid deformations over time and calculating the energies expended for each deformation, allowing for the identification of the forces that dominate the transition energies. The authors state that this approach has not been used before in continuum membrane mechanics and offers a viable framework for various membrane biophysics problems. The introduction ends with a mention of the materials and methods used in the study. Presents the mathematical model used to describe the energy of membrane fusion. The bilayer is assembled from proximal and distal monolayers, and in hemifusion, the monolayers of the hemifusion diaphragm are denoted. The energy of the bilayer is the sum of intrabilayer elastic contributions and long-range surface interactions between separate membranes. The elastic energy is defined by three independent deformations: splay, tilt, and stretch, which result from the local variation in lipid orientation and extensional order. The interactions between membranes are due to attractive van der Waals forces, repulsive hydration forces, and hydrophobic interactions. The rotational diffusion of the lipid body is well described by rigid body motion. The director D represents the average lipid orientation, and N is the surface normal directed outward from the bilayer core. The bilayer is assumed to be symmetric if the spontaneous curvature is the same in all monolayers. The energy of the reference state is the energy of two planar bilayers with the same total surface area. Shows the total energy, stalk energy, and barrier height as a function of various parameters. The total energy and stalk energy in symmetric bilayers decrease with spontaneous curvature. The barrier height increases with resting lipid length but is insensitive to it. Suppressing the extensional degree of freedom significantly increases the barrier height and stalk energy. Illustrates the energy profile for HD expansion. The energy of HD expansion is made possible by the presence of a second lipid component in the distal monolayer. For a single distal component, HD expansion requires energy because diaphragm splay increases with the radius of the HD. But with a second lipid component, hemifusion requires energy in distal splay, but the diaphragm continues to expand. Overall, these results provide insights into the energetics and barriers involved in various steps of membrane fusion. The calculations highlight the importance of spontaneous curvature, lipid length, and bilayer separation in determining the energy landscape of fusion. They also demonstrate the significance of distal monolayer composition in enabling HD expansion. These findings contribute to our understanding of the molecular mechanisms underlying membrane fusion and have implications for related biological processes. This scientific paper discusses the use of continuum theory to describe the steps of membrane fusion. The authors argue that continuum theory is reliable for describing monolayer and bilayer deformations because molecular collisions and interactions average out granularities. They find that explicit minimum energy shapes of fusion pores determined by molecular simulations are in excellent agreement with continuum theory. The authors also suggest that continuum theory accurately describes the static intermediates of fusion. However, they note that it remains to be seen whether continuum theory captures the physics of transition states or nanoscopic processes where only a few lipids are involved. The authors also discuss the assumptions made in their study and suggest improvements for future studies. They conclude that fusion pores do not form directly from a stalk and that hemifusion requires a small amount of energy. The authors also find that pores formed in the center of an extended diaphragm will expand. They compare their findings to previous studies and find that the energy barriers calculated using continuum theory are similar to those calculated using molecular dynamic simulations. Overall, this study provides insights into the energy barriers and mechanisms involved in membrane fusion. If you are an author or copyright holder for the work presented in this video and you have any issue with the existence or contents of this video, please let me know.